once again for the invitation to give a talk. Some of the results I will present are joint work with Lucia Bagnoli, and some other results joint with Alex Molev. So regarding my talk, it takes place in the area of quantum vertex algebras. So these are some structures, some vertex algebra-like structures, which can be associated with different classes of quantum groups. So the plan for my talk is I will start with two introductions. So I would like to say a few words in general on quantum groups. And then afterwards, another introduction, so a little bit about vertex algebras, some basics, with a special emphasis on the vertex algebras which come from affine Kac-Moody Lie algebras. And then these two introductions, they will actually serve as a motivation for the, the main problem I would like to talk about. It's how to establish connection between these two theories of quantum groups, theory of quantum groups, and theory of vertex algebras. So let's start a little bit with quantum groups. So what you can see here is the so-called quantum Yang-Baxter equation, which is, as I will explain later, closely related with quantum groups. Originally, it appeared in the context of statistical mechanics in late 70s. In the middle of the slide, you can see the precise definition of the quantum Yang-Baxter equation. So suppose V is a vector space, and throughout my talk, it will be complex vector space C to the n, so just n tuples of complex numbers. And suppose R is a linear map defined on the tensor square of V. Then this here identity of operators on the triple tensor product of three copies of V is called quantum Yang-Baxter equation. So what this notation here means is that by this numbers 1, 2, 1, 3, 2, 3 in the subscript, we just indicate on which tensor copies each of these copies of R should be applied. So for example, R1 means that we apply R on the first and the second among these three copies. So, well, any linear operator satisfying such an identity is then called the R matrix, and then this identity is called quantum Yang-Baxter equation. Also, sometimes it is called a star triangle relation. So star triangle relation is the same thing as Yang-Baxter equation. Below the definition, you can see a very, very simple example. So I wrote down two solutions of quantum Yang-Baxter equation. The first one is the identity, one tensor square of two copies of C to the n. And the second one is the permutation operator, more precisely the transposition. So it just swaps the first and second tensor factor. Throughout my talk, I will often use this matrix notation. So I denote by Eij the matrix, square matrix of order n, which at position ij, so n3 ij is 1, and all other entries are 0. So it's standard canonical basis of n C to the n. Okay, so aside from this quantum Yang-Baxter equation, there are numerous generalizations of quantum Yang-Baxter equation you can find in the literature. So here I wrote down two of them, which will be later on very important for the main topic of my talk. So at the previous slide, I said that R is a linear map on the tensor square of two copies of some vector space. And now suppose that this R is some function that depends on some argument, which I denote by U. So it can be, for example, a polynomial in U, or I don't know, rational function in U, maybe even formal power series in U in infinitely many positive or negative powers. And then coefficients with respect to this variable are linear operators over the tensor square of your vector space. So then I will refer to these two generalizations as additive and multiplicative Yang-Baxter equation due to the fact that in this here middle term, R13, we have addition that is the multiplication of the arguments of the variables. Below, you can see two solutions, one solution of the additive, one solution of the multiplicative Yang-Baxter equation. So this first example is probably the most well-known matrix, I'd say. It's called Yang matrix. So it is defined, as you can see, using this linear operators from the first slide. So I is the identity, P is the permutation operator. And here we have this term U inverse. So because of this term, which is essentially a rational function, 1 over U, this one, our matrix, is also called said to be rational R matrix. So this Young R matrix, it satisfies this first additive Yang-Baxter equation. Then below you can see the so-called trigonometric R matrix in type A. So you can see the explicit formula. So regarding this formula, you could think of it as being the this R matrix as being the rational function in two variables, Q and X. Or if you prefer, you could set Q to be some complex parameter, and then this R of X, its entries can be regarded as just rational functions in one variable X. Probably it's worth to mention that these two R matrices, although they do seem quite different, they are closely related. So by applying some substitutions to this trigonometric R matrix and then considering the top degree components with respect to some grading operator, you essentially obtain this Young R matrix, but it comes multiplied by some function. I think it would be this Young R matrix times maybe U over U plus 1 or something like that. All right, so here I included another example, but I would like to stress out that among all these R matrices, the one which we will need throughout my talk is this trigonometric one. So regarding this next example, so it is just to show you one elliptic solution of Yang-Baxter equation, but we won't need this R matrix later on. So here you can see the explicit definition for this R matrix. It's called the elliptic R matrix of the 8-vertex model. So its matrix entries A, B, C, and D, they are uniquely determined by these here expressions and by the requirement that A and B possess only even and C and D only odd powers of the variable Z. And actually, if you explicitly write down the expressions for A, B, C, and D, so they can be expressed in terms of Jacobi data functions, and that's because this R matrix is said to be elliptic. Okay, so quantum groups. The first examples of quantum groups that appear in the verse of Faddeev, Kozic, and Reshetikin in the context of quantum integrable systems. More precisely, these first examples, these were Yangians in type A. Then in mid-80s, independently, Drinfeld and Jimbo, they introduced a certain wide class of algebras, which were deformations of the universal enveloping algebras of certain Lie algebras, and these are today, well, referred to as Drinfeld-Jimbo type quantum groups. It soon became evident that quantum groups are related with many areas of both mathematics and physics, so I listed some of them here on the slide. And here in this remark, I would just like to, not very precisely, but briefly, explain how quantum groups are actually related with that quantum Yang-Baxter equation I was talking about. So suppose UQ is some quantum group, maybe, I don't know, Yangian or quantum affine algebra, whatever. And then suppose you have a representation of this quantum group over some vector space, which I denoted by V. Then this quantum group UQ, being the Hopf algebra, you can define the representation on the tensor square of V. So you use this coproduct map denoted usually by uppercase delta, coproduct or co-multiplication. And then on the other hand, quantum groups are required to be, roughly speaking, quasi-triangular Hopf algebras, which in part means that if you consider their tensor square suitably completed, perhaps, inside you can find a certain element, usually denoted with the uppercase R in this font, which is called the universal R matrix. And this universal R matrix then satisfies the Yang-Baxter equation over this triple tensor product of UQ, completed tensor product, which essentially means that if you suppose now you have some module for UQ and then you have the action of UQ on the tensor square as well, you can consider the image of this universal R matrix over this tensor square, and this will actually produce the solution of the Yang-Baxter equation. So sort of you could, well, think about quantum group as being a device for producing solutions of Yang-Baxter equation. All right, so this is what I was planning to say about quantum groups. Now just for a brief moment, let's forget about quantum groups. And now I would like to say a few words about affine vertex algebras. So I'll start by recalling some basic notions from theory of affine Lie algebras. So let's start with a simple Lie algebra, which is denoted by G. Suppose it's complex. For example, G can be SL2, like 2 times 2 complex matrices, so matrices with complex centers with trace 0. Then there is this well-known construction where you tensor your simple algebra with Laurent polynomials, and then you add this one-dimensional subspace spanned by the element uppercase C. So thus you get an infinite-dimensional space, and then this space can be turned into a Lie algebra with Lie brackets, which are defined as in this formula on my slide. So here we require that this uppercase C, this specific element, is a central element, so it commutes with everything, as you can see from this second identity. And here's the well, precise definition of the Lie bracket on the corresponding loop algebra G tensor by C of TT inverse. So this brackets here, they indicate the it's called killing form for simple Lie algebra. Right, one other thing we'll need is the universal enveloping algebra of G hat, which I will denote by U of G hat, and which, thanks to PBW theorem, contains G hat. And then here in this definition, so you can see one well-known construction from the representation theory of affine Lie algebras. So we choose an arbitrary complex number, lowercase c, and then we construct, so it's called vacuum module, or sometimes generalized Verma module. So it's defined as the quotient. So we take the enveloping algebra U of G hat, and then take the quotient over its left ideal. And this left ideal is generated by the elements from affine Lie algebra, which possess only non-negative powers of t. And in addition, we take this element here, uppercase C, so central element minus C times 1, in order to ensure that the central element acts as multiplication by lowercase c. Hence, we say that this vacuum module is of level C. All right, so now just one slide on vertex algebras in general, and then I will show you some results on affine vertex algebras, those which are related with this Lie algebras from the previous slide. So regarding vertex algebras, they were introduced also in mid-80s, as with quantum groups. They were introduced by Borchardt. So you can say that they generalize both the notions of commutative associative algebra and also the notion of Lie algebra. And they also are related with many areas of both mathematics and physics. So what you can see here on this slide, it's not a precise definition. I omitted some axioms, but I just wanted to show you some of them, which will be very important for the main part of my talk. So roughly speaking, you can think of vertex algebra as being a pair. So we have, let's say, two pieces of data. So first one is a vector space. Throughout my talk, it will be complex, infinite dimensional. And Y is a certain map, linear map, which is called vertex operator map, and which maps each vector of this space V to a formal Laurent series in one variable, which you denote by Z. And the coefficients of this Laurent series, which you denote like this, A sub n, are linear operators from V to V. And then this vertex operator map, it is required to satisfy some properties. The key property is this, locality, which says that for any two elements of your vertex algebra, A and B, you can find an integer r greater than or equal to 0, such that these two expressions coincide. Also, there's this other property. So usually when you, I don't know, look some textbook on vertex algebras, You probably won't find weak associativity in definition of vertex algebra. That's because it can be derived from other axioms. However, I wanted to include it here, although this is quite redundant, because we'll need this weak associativity later on. So what this property says is that so for any three elements, A, B, C, in V, you can find a non-negative integer R such that these two expressions coincide. So when I said earlier that vertex algebras can be regarded as generalizations of commutative associative algebras, so notice that here in this locality property, so you have vertex operator of A applied on vertex operator on B, and on the right-hand side, vertex operator on of B applied on vertex operator of A. So if R were 0, then this would be actually commutativity. And on the other hand, this weak associativity property. So what happens on the left-hand side is that vertex operator of B acts on C, and then vertex operator of A is applied on what we get. And finally, on the right-hand side, the vertex operator of A is acting on B, and then this entire expression, its vertex operator is then acting on C. So it looks like that's ordinary notion of locality. Also, you can combine these two properties to derive another property, which is called Jacobi identity, which looks a little bit more complicated than these two, but it sort of resembles the Jacobi identity from the definition of Lie algebra. That's why we say that vertex algebras generalize Lie algebras. Okay, so now one slide about certain class of vertex algebras which come from representation theory of affine Lie algebras. So on this slide, suppose G is a simple Lie algebra, complex, and by H check I denote the dual Coxeter number of G. So for example, if G is SLN, then H check is just N. So there's this well-known result of Igor Frankl and Yongchang Zhu from 1992. So suppose C is a complex number, then this VC of G, the vacuum module, as I defined it 2 slides ago, can be naturally equipped with the structure of vertex algebra. And then this vertex algebra is called universal affine vertex algebra, and this universal actually indicates the following. So if you have any restricted module for G hat of level C, then this module can be equipped with the structure of module for vertex algebra, VC of G, and vice versa. So if you have a module for VC of G, then it naturally becomes a G hat module, which is restricted, and it is of level C. And also, in addition, so the module is reducible with respect to the action of one of these structures, if and only it is irreducible with respect to the other, to the action of the other structures. So you could say that sort of representation theory of G hat and VC of G hat, then C goes over all complex numbers, that they coincide. All right, another result I would like to recall from the same year, it's due to Boris Fagin and Edward Frankel. Actually, before I start to state this theorem, so I'd just like to recall that, well, as with, I'd say, many other algebraic structures, there is natural way to introduce the notion of center of vertex algebra, and then straightforward, directly from the axioms, you can show that this center is naturally equipped to the structure of commutative associative algebra. That's something that's easy to prove, just a little computation. And then what Fagin and Frankel theorem says, so it actually completely describes the structure of the center of the affine vertex algebra at the critical level. So when this C is said to be minus H check, so it says that it's isomorphic to the algebra of polynomials in infinitely many variables. And then this, in honor of this result, this center at the critical level is usually called Fagin-Frankel center. Right, so although this theorem does completely describe the algebraic structure of the center of affine vertex algebra, it's perhaps worth noting that it's still not evident from the theorem how to, for example, create the how to obtain some families of algebraically independent generators. So the center for different types, the so-called Segal-Sugawara vectors. And then this problem was solved in several papers. Some algebraically independent families were constructed by Chervov-Dalalayev and Chervov-Molev in type A, then by Molev in types B, C, and D, and also by Molev, Ragostina, and Rozhovska in type G. Okay, so finally we come to the problem I would like to talk about. Back, well, rather soon, a few years after the invention of quantum groups, appeared this paper by Frenkel and Jing, where they explicitly defined realization of certain level 1 modules, the so-called basic modules, that is integrable highest-weight modules, for quantum affine algebras in types A, D, and E, simple A's types. And their realization, this Frenkel-Jing realization, it resembles the realization of level 1 modules for the corresponding affine Lie algebras, which goes back to Frenkel, Katz, and Segal. And motivated by this, they ask a question whether one can somehow associate some vertex algebra-like structures to quantum affine algebras and other quantum groups, so that they sort of correspond to representations of quantum groups in a similar fashion as this results from my previous slide, where vertex algebras and their representations are related with representations of affine Lie algebras. Regarding this diagram here, so this fact that affine vertex algebras and affine Lie algebras possess similar representation theory is indicated by this here arrow. On the other hand, by deforming or quantizing enveloping algebras of affine Lie algebras, you obtain some quantum groups, for example, quantum affine algebras or Yangians, and so on. On the other hand, there is a path where you can go from this, let's say, quantum theory. So the top of the diagram corresponds to the quantum theory, back to the classical theory. So it's known as classical limit. So for Yangians, this means that the deformation parameter h goes to 0, or for quantum affine algebras, that's this q, which appears in their definition, which I will show you later, goes to 1. And then this dashed arrows, they indicate some things which people hope to hold, but they're not evident at that time. So roughly speaking, the question is whether you can somehow define some, let's say, quantum vertex algebra, some vertex algebra-like structure, such that, so first of all, it can be regarded as some quantum version, some deformation of the affine vertex algebra, and whether it's possible that this quantum vertex algebra somehow is related with representation theory of quantum affine algebras in a similar way as we have here at the bottom of the diagram. So the key, let's say the key problem, the key obstacle here is, here we are, is that if you consider vertex operators which arise from representations of, say, quantum affine algebras, for example, from these vertex operators which are constructed by Frenkel and Jing, they're simply not local. So they do not possess this locality property. And that's actually the reason why you cannot simply attach the vertex algebra theory to quantum groups, but rather you need some different new, let's say, more general structures. Okay, so this slide, so it's definitely incomplete, but very brief summary what was going on regarding the development of quantum VA theory. One of the key papers is the one of Edward Frenkel and Nikolai Reshetikin from 1997, where they introduced the form chiral algebras. And then soon after, so there was this series of papers, I think there are 6 of them, of Etingof-Kazhdan on quantization of Lie algebras. And 5th paper in the series from 2000. In this paper, they introduced the notion of quantum vertex operator algebra. And in addition to the definition of this notion, they constructed first examples of quantum vertex algebras. There's also another approach to the development of quantum VA theory, which is due to Borchets from 2001. And this one was actually further extended quite recently in 2023. This, as you can see, second row from the bottom of the slide. So Kozic in 2023 introduced the so-called categorical quantum vertex algebras, which extends sort of this approach of Borchets. Then in 2003, two papers appeared. So Bagnoli and Kozic introduced the notion of field algebras, and Li the notion of axiomatic G1 vertex algebras, which are today called non-local vertex algebras. So both of these structures are something much more general than vertex algebra. Actually, I can show you. So simply in this definition of vertex algebra, you erase the locality, so you omit this key property, but you keep the weak associativity. So this is something very general, and roughly speaking, the idea was to try to first better understand these very general structures, and then afterwards further specialize these notions. All right, so I should also say in 2009, there's another approach. So Anguello and Bergwelt, they introduced HD quantum vertex algebras, which generalize Etingof-Kazhdan's theory. And in 2011, Li introduced the theory of pi-coordinated modules. So it turns out that in this setting of quantum affine algebras, as I will explain in more detail later, it turns out that the ordinary notion of module is not good. It's not useful. But you need to consider something that can be regarded as, let's say, deformation, or maybe it's better to say generalization of the ordinary notion of module. And this turns out to be the right setting to attach quantum vertex algebras to representations of quantum affine algebras. So among all these other papers, I would just like to point out, so there's actually a series of papers by Jing Kong, Li, and Shab in 10, and also in addition this paper of Kong a year later, 2023. And these papers actually solve in full generality this problem of Frenkel and Jing. So they introduce several new concepts in the theory, such as equivariant phi-coordinated modules, the concept of deforming vertex algebra by vertex bialgebra, and finally they completely developed quantum VA theory both for quantum affine algebras of untwisted and twisted types, and also some other generalizations. Also, more recently, quantum VA theory, so in 2024, was associated with quantum toroidal algebras in type A. Okay, so what you can see on this slide, so it's a sketch, not a complete definition, of the notion of quantum vertex algebra as defined by Etingof and Kazhdan in 2000. So first difference you can see in comparison to that definition of vertex algebra I show you is that I'm saying quantum VA is triple. So now we have like 3 pieces of data. So originally in definition of vertex algebra, V is a vector space, and now V is a topologically free COH module, meaning it is so separated, torsion-free, and complete with respect to the H-adic topology. This uppercase Y, this is still a vertex operator map. Now it's COH linear, so I'm using the same notation as before. And finally, we have something new, this map S. So this map S, it's called braiding. It's called braiding due to the fact that it is required to satisfy the additive Yang-Bak's equation, the one from the beginning of my talk. You can see it written here again in terms of this operator S. So now, natural question at this point would be, why do we need this? What do we need this braiding for? So it turns out that this braiding actually governs the so-called S locality property. So this is the quantum version of that locality property, which appears in the definition of vertex algebra. So as I said, the vertex operators coming from representations of quantum affine algebras, they are not local, but they are, let's say, S local. So what this S locality property says is that for any 2 elements, A, B in your quantum VA, And for any n non-negative integer, you can find a negative integer r such that these two expressions, they do not necessarily need to be equal. So perhaps you cannot find r so that the first expression equals the second expression. However, for any non-negative n, you can find r such that they coincide modulo h to the n. So it's sort of topological generalization of the locality, topological in the sense of H-adic topology. There's also this weak associativity property. I didn't include it here, but it's of the same form as in the definition of vertex algebra, except again the H-adic topology is involved. So you would say here that for any ABC, for any n, you can find r such that these two are equal modulo h to the n. So the reason why in this definition of vertex algebra you don't see that map S is another property in the quantum VA definition. So at h equals 0, so at the classical limit, S goes to 1. So S just becomes the identity. However, Etingof-Kazhdan, they introduced in that same paper a notion of quasi-classical VOA. So this is, roughly speaking, vertex algebra, but which is equipped with some kind of braiding. And at this quasi-classical limit, so it's something that sort of remembers more information than this classical limit, this map S, which here is a solution of quantum Yang-Bak's equation, at the classical limit, it produces another map, which is not an identity and which is actually a solution of the classical Yang-Baxter equation. Okay, so here is the definition of quantum VA. And now I would like to show you how you can associate such object, quantum VA, with the trigonometric matrix. It's exactly the trigonometric matrix from the beginning, from the, I believe, second slide of my talk. So we start with this trigonometric matrix. What I'm showing you now, it's actually Etingof-Kazhdan's construction, so how they constructed this first example of quantum VA. So we start with this trigonometric matrix we've already seen. So I already mentioned it satisfies the multiplicative Yang-Bak's equation, one you see here at the bottom of the slide. So obviously this matrix does possess one, there is one problem related with this matrix. So the quantum VA should be something that's in particular topologically free C of H module. So now we want to adapt this matrix so that it is given not over the C of Q, so over field of rational functions in Q, but over C of H, so commutative ring of formal power series in variable H. So we make one adaptation, one change to this matrix. We define another matrix, H of X, which is essentially what you get if you take the original matrix from the previous slide, and then you just everywhere you replace Q by formal power series e to the H. So now this gives you the matrix, which is given over the commutative ring C of H. Now, what these expressions here mean is that these expressions which appear in the denominator, you need to expand them in non-negative powers of H. So this matrix, again, it satisfies the, well, not surprisingly, multiplicative Yang-Bak's equation. However, in this quantum VA construction, so as I said, sort of the key property in the definition of quantum VA is this S locality, and somehow we want to use this trigonometric matrix to define this braiding. However, the braiding, it satisfies the additive Yang-Bak's equation, while the trigonometric matrix satisfies the multiplicative one. And now we want to sort of make it additive, so to say. So we make another change to this matrix. So inside of this substitution, Q equals e to the H, we make another substitution, X goes to e to the U, so formal power series in U for the exponential function. And thus we get the matrix, again, over C of H. So I just replaced all appearances of X by e to the U. And the meaning of these expressions is, again, well, same as on the previous slide. You just expand everything so that you get non-negative powers of x, and you will get both non-negative and non-positive powers of u in your expansions. And now this matrix R of u is one we will use in construction of quantum VA. And it satisfies the additive. This is the key part. It satisfies the additive Yang-Bak's equation. So this one here at the bottom of the slide. Okay, so this definition, this is also due to Etingof-Kazhdan. So they introduced so-called quantized universal enveloping algebra. So you can think of it as being the quantum counterpart of the associative algebra structure over the vacuum module VC of G, which I introduced several slides ago. So the precise definition is as follows. So it's a h-adically completed associative algebra over C of H. Its generators are these elements Tij of minus R. Ij go from 1 to n, and R goes over all positive integers. And regarding the definition, so it's probably the best to read it from the bottom to the top. So first we take these generators, Tij of minus R, and we organize them into formal power series, Tij plus of u, like this. So we end up with n square such power series. And then next we organize this formal power series into square n times n matrices. And then this here, well, rather simple identity is the identity of formal power series in variables u and v. And the coefficients of this series belong to this triple tensor product, 2 copies of matrices and 1 copy of this u of r. And by these numbers, 1, 2, 1, 3, 2, 3, we just indicate on which tensor factor each of these elements should be applied. Okay, so this R1, 2 is actually redundant because R can be only applied on first and second tensor factor. But this 1, 3 and 2, 3 do indeed carry some information. So T1, 3 means that this T plus of u is applied on the first and on the third tensor factor. T2, 3 that this other copy is applied on the second and the third tensor factor. So in order to actually extract the defining relations, what you would need to do is to, so you fix some R and S, powers of u and v, and then you equate the coefficients of the same powers on the left and right hand side. You end up with some identity in this here triple tensor product, and then you want to get rid of these two auxiliary spaces, so just equate the matrix entries, the same matrix entries on the left and right hand side. But once you do it, then this relation becomes much more complicated. Okay, so here is the Etingof-Kazhdan's construction of quantum vertex algebra. So I included all the formulas, but I don't really want to explain all the details. So what they did, so for any complex number C, they show that there exists unique quantum vertex algebra structure over the C of H module of U of R, the one introduced on the previous slide. This quantum vertex algebra, it's denoted by VC of GLN, and they actually give explicit expressions both for the vertex operator map, it's written like this, and also for the braiding, the one which satisfies additive Yang-Baxter. All these expressions which appear in these two formulas, they are precisely defined below. But what's worth perhaps mentioning is that this Tn plus, it's roughly speaking quantum version of creation operators, Tn minus quantum version of annihilation operators. And here one funny thing occurs. So this Tn minus, I didn't define it anywhere. It's just some operator over U of R, but I didn't show you the definition. One funny thing is that in this quantum setting, annihilation operators, they have infinitely many negative, but also infinitely many positive powers of Z. So something which does not happen with affine vertex algebras. Regarding the braiding, so just note that there are lots of matrices here involved. Roughly speaking, braiding is defined in terms of this matrix products, and then thanks to the fact that this matrix satisfies the additive Yang-Baxter equation, the same holds for the braiding as well. Okay, so what actually Etingof-Kazhdan did, so they carried out this construction both for the rational, trigonometric, and elliptic matrix in type A. And at the classical limit, what you get from this quantum vertex algebra is just ordinary universal affine vertex algebra, which was obtained by Frankel and Zhu in 1992, that construction I mentioned earlier. Later on, we generalized this construction to the types B, C, and D, so orthogonal and symplectic types, joined with Jing and Mariana Buteratz. And now that diagram, which represented the main problem I would like to discuss. So some parts of the diagram are now completed. So here we have this quantum VA of Etingof and Kazhdan. Its classical limit is the ordinary universal affine VA. On the other hand, we have quantum affine algebras, and well, natural question at this point would be whether these two objects at the top of the diagram, whether they are somehow related. So here we, as I mentioned earlier, GLN hat and VC of GLN, they have the same representation theory. So it's natural to try to somehow connect representation theory of quantum VA, VC of GLN, and of quantum affine algebra, UQ of GLN hat. Right, so in order to, well, establish a connection between these two, it turns out that we need two more ingredients. So the first one is a suitable realization of UQ of GLN hat over the commutative ring C of H, and I will show you this realization in a moment. And the second one is this pi-coordinated module theory of Hai-Sheng-Li, so I will say a few words about it as well. So regarding the realization of quantum affine algebra, so the one which we need, the so-called A-matrix realization, or RTT, RLL realization, it was given by Reshetikin and Semyenov-Tiamshansky in 1990. So you can see here precise definition. So it's slightly adapted in comparison to the original version, so that it is given over the commutative ring C of H. So we have like two families of generators, Lij of R, Lij of minus R, and in addition, one Moog generator, which is required to be central. And then, as with this definition of universal enveloping algebra of Etingof and Kazhdan, we organize these generators into two formal power series. Then, not two, but 2 times n squared power series. Then we arrange this power series into square matrices of order n. And then once we've done with this, we can write down defining relations in this compact matrix form. So again, indices 1, 2, and 3 indicate as spaces. So we have 2 copies of matrices of order n and 1 copy of quantum affine algebra. All right, so one more notion we need is the notion of restricted module for quantum affine algebra. So this, what you see, is actually a straightforward generalization of the notion of restricted module for affine Lie algebra. So we say that the module is restricted if it is, so first of all, we want everything to be topologically free. So is this module. And this restricted actually indicates that when you apply this L minus of x, so this is one of these two generator matrices, the one with, as you can see from the last line, the one with negative powers of x only. So when you apply this matrix with negative powers of x on W, so we can actually get an essential singularity. But what we want is that when this is regarding modulo h to the n, that only finitely many negative powers appear. So only poles modulo n for every n. And of course, in addition, we say this restricted module is of level C if this canonical central element acts as a scalar multiplication by number C. So one example of such module would be vacuum module for the quantum affine algebra at the level C. So it is restricted. So one more remark. So suppose we choose some restricted module for quantum affine algebra. Let's denote it by W. Then, so Reshetikhin and Semyonov-Shamsky in their paper, they define this here operator, L of x over W. This H here in the subscript, I didn't introduce this notation earlier. It just means h-adic completion. So W is h-adic topologically free. You take W of x, so formal power series in x with infinitely many positive and finitely many negative powers, and then you complete it h-adically. This is what this H means. So they call this L of x quantum current operator, and they show it follows from this RLL relations from the 2 slides ago that it satisfies multiplicative quantum current commutation relation. This one in here. On the other hand, if you consider, so by T of u, I denote this here product T plus times T minus inverse, where T minus comes shifted by HC half. So this expression here on the right is actually a special case of this expression from Etingof-Kazhdan's construction, which uniquely determines the vertex operator map. So this expression, it satisfies again quantum current commutation relation, but it's additive counterpart. So notice here that we have division between arguments y over x, x over y, while here we have some addition or subtraction. So sort of this identity, it happens in the representation, it occurs in the representation theory of quantum affine algebra, and it's multiplicative. On the other hand, quantum VA is essentially additive structure. So the locality takes, this is actually the locality in Etingof-Kazhdan's quantum vertex algebra. So now the question is, how do we compare these two structures? So one is sort of multiplicative, the other one is additive. So this problem was originally observed and also resolved by Haisheng Li. So first of all, I would like to point out that for quantum vertex algebra, there is a natural way to introduce the notion of module for quantum vertex algebra. So the definition, you can see it here. So it's just module is topologically free C of H module equipped with some map which maps elements of quantum VA to formal power series whose elements are linear operators over this module. And then this map needs to satisfy some properties. The key property is weak associativity. So actually this property looks slightly different than that weak associativity property I showed you before. The reason for this is that this perhaps slightly unusual form of weak associativity is useful for generalizations, as you'll see in the next slide. And it was showed, I think, by Haisheng Li, Xiaobin Tan, and Qing Wang that this version of weak associativity is actually equivalent to that ordinary form of weak associativity. So here actually we have two statements, so that for any n and for any elements u and v, you can find a negative r such that, so first of all, this expression when modulo h to the n, when regarding modulo h to the n, admits this substitution, so that this substitution, at least modulo h to the n, is well defined. And in addition, when you carry out the substitution, you get something that coincides with the right-hand side, again, modulo h to the n, so some kind of topological generalization of the ordinary weak associativity. And it turns out that this weak associativity I'm showing you right now, it doesn't work, so it doesn't allow for the establishing connection between VC of GLN and representations of quantum affine algebra, exactly due to this issue where on the one side you have something multiplicative and on the other side you have something additive. However, this was resolved, it was 3 years later by Haisheng Li, so he introduced the notion of phi coordinated module. If V is a quantum vertex algebra, then there's this notion of associative formal additive group. So it is just a formal power series in two variables, denoted by Z2 and Z0. And this series satisfies these two simple properties. And then for each such phi, you can consider the notion of phi coordinated module. So if you want to compare this definition of phi coordinated module to the with the definition of module from the previous slide, so the only things that change are those which are colored in red. So now in the previous version of associativity, Z1 went to Z2 plus Z0. Now instead of that, we have phi of Z2, Z0. And in the previous version, we had Z0 to some power R. And now we have difference phi minus Z2 to power of R. And in fact, in this more general definition, if you set phi to be Z2 plus Z0, you actually go back to the previous definition, you obtain the ordinary notion of module. However, it turns out that this ordinary one is not the right one, so we want to consider another phi, another associate of formal additive group. Okay, so this particular phi, this associate Z2 times e to the Z0, so it was originally suggested in Yangians' paper. So for this phi, you can show the following. So you can show that restricted modules for quantum affine algebra of level C are the same as phi coordinated VC of GLM modules, meaning that if you have a module for one structure, then you can actually define on it a structure of module for another structure. And in addition, a module is reducible with respect to one action, if and only if it's irreducible with respect to the other action. So here I just included one formula so that you see where the that quantum current operator, where is it? Where that quantum current operator L of x of Reshetikhin and Semyonov-Tershansky appears. So here is its definition in terms of generators of quantum affine algebra. And in fact, this phi coordinated module map, which emerges here in this theorem, if you apply it on this generator matrix of the algebra U of R, that algebra, quantized universal enveloping algebra of Etingof-Kazhdan, so it just maps this matrix to that quantum current operator of Reshetikhin and Semyonov-Tershansky. However, you need to do this substitution on the operator, and what this substitution essentially is, it's this this associate of the one-dimensional additive formal group. So one problem with this result is that it heavily depends on the matrix realization of quantum affine algebra. On the other hand, much more general results were obtained in this series of 3 papers by Naiwan Jing, Fei Kong, Haixing Li, Xiaobin Tan. So they completely developed the quantum VA theory for all types of both untwisted and twisted quantum affine algebras, so both in this type A and all other types. And this result also, it fits not so much this matrix realization, but rather Drinfield's new realization of quantum affine algebras. It may be even better, easier to use it in combination with representations of quantum affine algebras, as most of them are given in this Drinfield's new presentation. Okay, so if you recall back maybe half an hour ago, when I was talking about some results in the theory of affine vertex algebras, I mentioned that there's this Fagan-Frankel theorem on the form of the center of quantum affine, not quantum, but universal affine vertex algebra at a critical level. So back in 2017, joint with Alex Molev, we wanted to check whether something similar holds for this quantum VA of Etingof-Kazhdan. So this is our result. So first I start with the definition of the notion of center. So the center of quantum VA is defined like this. So it consists of all elements A of quantum VA, such that when you apply vertex operator on them, you get only non-negative powers of Z. So axiomatics of quantum VA allows here for infinitely many both positive and negative powers. However, modulo h to the n, there should be only finitely many negative powers for every n, and then element is in center if it produces no negative powers, so no even poles. Right, so what we actually did, maybe I don't want to go through all these details. So this pH, this is just some it's called H permutation operator. So if you set H to be 0, then you get that usual permutation operator from my first slide, I believe, which was solution of quantum Yang-Box equation. So using this H permutation operator, you define some K cycle for any K. D here stands for a certain diagonal matrix. If you're interested where this matrix, not a matrix, but just matrix, where this matrix comes from, it comes from the so-called crossing symmetry property of the trigonometric matrix. So what we managed to do, joint with Molev, is so at the critical level, so when C is equal to level C is equal to minus n. So we constructed a certain family of algebraically independent generators of the center, denoted by phi m of r. Of course, at the classical limit, this phi m of r will produce algebraically independent generators of the Feigenfractal center, so center of the ordinary affine vertex algebra at the critical level. Here you can see the explicit expressions for these elements. So you have this K auxiliary spaces of matrices. So you multiply all of this, and then you apply the trace over the tensor factors 1 to K, somehow adjust these coefficients, and you get formal power series, more precisely n formal power series phi m of u, such that the coefficients of this series are algebraically independent generators of the center. And also we show that the center of this particular quantum VA is naturally equipped with the structure of commutative associative algebra. So essentially what happens is that it's again isomorphic to the not precisely algebra of polynomials and infinitely many variables, but the H-ad completion of such an algebra. So that's what happens at the critical level. At the non-critical level, as we will consider not SLN, but GLN, so center is not trivial, but it is much smaller. So there's this notion of quantum determinant, which appeared, I believe, in definitely in 80s in the context of Yangian. So here for this quantum VA, VC of GLN, you can also define the quantum determinant. So it's just product of these matrices. You have this additional diagonal matrices from the previous slide. And uppercase A with superscript n, it indicates the action of the normalized anti-symmetrizer. And then if you denote the coefficients of this quantum determinant like this with delta R, then it turns out that these coefficients at the non-critical level, the coefficients are algebraically independent generators of the center. Okay, so there was another topic I was hoping to have enough time to talk about, but I think it's better I don't start with it. So it's more recent research with Lucia Bagnoli on reflection equation, which goes back to a famous paper of Sklianin from 1988. So roughly speaking, what we noticed is that this quantum current commutation relation of Reshetikhin and Semyenov-Tershansky is of a similar form as this reflection equation, which is often used in the literature to introduce certain algebras. For example, there are these twisted Q Yangians, which are co-ideal subalgebras and quantum affine algebras. So we sort of managed to introduce some deformation of phi-coordinated modules. So definitely don't want me to go through this definition at this moment. And we show that actually these structures can be again used to compare, on the one hand, representation theory of this Q-twisted Yangians, and on the other hand, this deformed representation theory of Etingof-Kazhdan's quantum vertex algebra. Okay, so I will stop here. Thank you for your attention.
Thank you very much.